This is a talk co-authored by my colleagues from Waters, Kathleen Tonanu, Hans Wisses, and others. At this conference, it's the last day, you have seen a lot of different oligonucleotides and molecules. So we know how to deal with the short ones, even if they are modified and so on. But now we have to look at the longer ones, let's say up to 100 mer or even longer, or mRNA that is 1,000 or thousands of nucleotides long. So on behalf of scientific community and analytical community, I must say we enjoy the challenge. How far we can push just a regular ion pair reverse phase chromatography? I do like the hexylammonium acetate system, so if you choose very efficient column and long column, shallow gradient, and an appropriately chosen, more hydrophobic ion pairing agent, you can push the separation, let's say, up to 70 mer. N-1 separation is beautiful. You can push it further, let's say, to 100 mer, and then the separation, of course, declines. And this is about as far as I can go. This method is good enough for sgRNA, 100 mer molecules. You can do routine analysis. The purity of this synthetic sample that I get from vendor was about 18% for the main peak. And we can, of course, use it for lab scale purification. In this case, I show you just 4.6 millimeter ID column, but you could use wider prep columns if you have to. And this shows an example how when you start from nanomole to tens of nanomoles, I can easily push it to 100 nanomole in a single injection. Yes, the peaks are getting fat. If you are not greedy and you start collecting just the narrow fraction for the main peak, you will get your 80 plus or 90 plus purity. And this is very much achievable, even if those oligonucleotides are modified. This is an application that we published in 2023, and this is, as far as I can resolve, homo-oligomers. This is a poly-A tail that has been cleaved from mRNA, and those are about 100 to 150 mer long, and it is known that there is a microheterogeneity of poly-A tail, so I can measure it. The blue chromatogram is from EPO, red chromatogram is fluciferase beta. Separation is not to the baseline. Nevertheless, I can see the separation, and when I spike the standard, I can really assign very easily what is the length of those oligonucleotides. And as you can see on the black chromatogram, we have up to 100 mer, we really have a N- separation. So this is very achievable. Let's push it further. This is an example that I did recently, and those are standards of single-stranded RNA. This is a standard. And you can see that we can push it, let's say, separation up to 1,000 nucleotides is really good. And no longer you have a chance to separate N-1 or even N-50, but this is a useful separation. The blue chromatogram shows the same chromatographic conditions for 500 mer up to 9,000 nucleotides long. And then you can see that the separation quickly falls off. This is not the feature of pore size. This is not a feature of mode. The same thing will happen for ion pair reverse phase, ion exchange, Higg, whatever you use. And basically, the separation selectivity falls off somewhere for the greater than 2,000 nucleotides long. Yes, I can adjust the gradient. Yes, I can use shallow gradient and optimize the separation. And I will achieve separation, let's say 7,000 from 9,000, but it is not going to give me a wonderful separation. So this is where the limitations of adsorption chromatography are. So what can we do? Let's have a look at size exclusion chromatography. That's the mode that resolves molecules by size. In this case, I'm showing just 100 mer, 60 and 30 mer. Those are oligo A standards. This is from the same publication I already mentioned. I'm trying to measure the length of my poly A tail. But in process of doing it, as I was ordering these synthetic standards from vendors, I realized that I actually can use size exclusion chromatography to monitor purity of my oligonucleotides. See the black chromatogram, the 100 mer. All of these later eluting peaks, those are short mers. The same sample on the upper right corner is analyzed in ion pair reverse phase chromatography, and you can see that I do achieve much nicer resolution. But when I look at the main peak and integrate it carefully, I get about the same estimate of purity. So size exclusion, even though it is, this is a disclaimer, low resolution chromatography, still could be useful. Especially, it could be useful for some of the very large RNA molecules. You just need to choose the column with the proper pore size. So upper chromatogram shows column with 450 angstrom pore size. So in this case, we actually start to include some of these long molecules in the pores, and we have separation that is really useful for this range of mRNA, let's say between 6,000 down to a few hundred. You can monitor the fragmentation of mRNA. The newer column that we recently launched has 1,000 angstrom pore size, and for that one, you can push it perhaps to a little bit longer mRNA molecules. When I told you we can use low resolution technique, size exclusion, I told you that we have problems with very large molecules in adsorption chromatography. What else can we do? And one of the methods was coined by Moderna in 2018 paper, this so-called mRNA mapping. So what do you do if you have a large molecule? It is heterogeneous, you cannot do very well LC-MS, and separation doesn't work much. You take it, you chop it with selective enzymes into shorter oligonucleotides and convert this difficult task into more difficult task. But at least we can resolve these short oligonucleotides and have LC-MS compatible conditions. So I did this analysis. This is about 2,000 nucleotide long mRNA, and you can see that we have a wonderful mRNA map. It gets a little tricky when you think about this mRNA mapping. So this has been clearly inspired by peptide mapping. Peptide mapping is a wonderful technique. You chop your protein with trypsin or lysine, you get unique mass peaks, and they are often very well resolved. Those are one of the most wonderful chromatograms that you can see in literature, and everything works. But if you do it the same thing with mRNA that has only 4 building blocks, you get peaks like the ones that I labeled, 30 mer down to 16 mer. They have all unique mass, except of that 16 mer that coincidentally had another peak that colludes that is exactly the same mass, just a slightly different sequence, but the same mononucleotide composition. So you end up with this isobaric peak. Still good. If you go to short oligonucleotides, and there is a lot of them, this mRNA mapping was done with T1 RNAs, so it chops after every G, and let's say you have a 25% of Gs in your sequence, you will end up producing a lot of short mers. So these short mers are no longer isobaric. Many of them have the same mass. They're often not chromatographically resolved, and when you go below 6 mers, there are many, many sequences that repeat somewhere in the sequence of your mRNA. So what do you say? They all collude, they all have the same mass and sequence. Does it serve as a mass and sequence confirmation? I have my doubts. So those are the limitations of mRNA mapping. If we do peptide mapping and we get less than 98% sequence coverage, we get a little bit nervous. In here, we live with a unique MS, signal about 38% coverage. If we include much more complex MS analysis of those peaks, we get about 56% coverage. So those are the limitations that we live with. One way how to handle this, and we thought this is going to be smart, is if you look at the upper right chromatogram, that's a detail of that other chromatogram, you see that there are occasionally some small peaks in this chromatogram. Question was, are these missed cleavages, missed cleaved oligonucleotides, which would extend your unique peaks, and then you would get a much nicer sequence coverage. So we thought about it and did the search, LC-MS search, that was extended by 1, 2, and 3 missed cleavages. If you have about 100 peaks that are the right cleavages, complete digestion, and then you include 1 up to 3 missed cleavages, instead of 100 peaks, now you are searching well over 1,000 potential candidates. And your search algorithm will do everything to assign those small peaks, and they were assigned, but are they correct? Another lesson learned from proteomics, we learned that you could use retention prediction. Based on peptide sequence, you can predict their retention. And you can use it as a filter of false positive identifications. On the left bottom corner, we did exactly that. We have an algorithm that predicts a retention of our oligonucleotide from its sequence, nucleotide composition, and it actually works. It works much better than I hoped. And then we applied it to these so-called miscleaved identification. Those are the orange data points. And as you can see, they are all outliers. So at this point, I say this is a failed attempt. All these minor peaks that we thought might be miscleavages, they are not. If we look at even like by MS at those peaks, we realize this is really not the right identification. So at this point, I say miscleavage is maybe not the best idea. Finally, I get into the same method applied to, let's say, guide RNA. It's about 100 mer. I show here 80 mer. If we apply the same method, can we get something useful? And I say yes. So when I apply RNase T1, it digests my 80 mer. The sequence is at the bottom. After each G, it cleaves. And on the right side, there is a list of putative peaks that should be there. And I do find them all. And there are very little other signals there. So this looks like, even by just LC-UV, this looks like a good method to check for the quality and sequence of your guide RNA. Because I'm a scientist, I chose the sequence such that peak 9A and 9B, those are 2 different clips, have different sequence, but they are also isobaric. They also coalute. So what do I do if there is such an occurrence in my chromatogram that I have isobars? I could use LC-MS. To do that, you will have to have some decent software. We use Confirm Sequence from Waters. There are other options out there. But you take the peak, you shake it, collision-induced dissociation, as opposed to trying to sequence 100 mer, which is very difficult. Now we have like 10 mers. It's brutally simple. We get full sequence coverage confirmed by many ions, and it works. I show you an example of another peak with, I zoom on the baseline, and you can see the entire Y series are there. C series, except of C1 is all there. And if you click, the software enables you to click on those ions and investigate your raw data. And you can click one after another and manually verify if you trust that identification. And I do. So I told you that I was investigating the miscleavages as a potential way how to fill the gap. Yes, I like the RNase T1 digest, but I am aware that it produces quite a lot of short, not very informative sequences. Can I actually extend, can I use the miscleavages for these short oligonucleotides? And when I say short, this is still 50 to 100 mers. So what I did was I prepared my sample, I spiked my RNase T1, shake it, put it in a carousel, and immediately start the run. The time of digestion was 25 degrees C, room temperature, for 4 minutes. So in 4 minutes, the red chromatogram is the result. My 50 mer, my original peak, is still there. It's not completely digested. I like that. And you can see that there are many peaks that are labeled with a red label. And those are the long ones. Those are truly miscleavages. And I find them. They have a unique mass. We can also sequence them. So I am able to create and use the missed cleavages. When I let the same sample sit in my autosampler and immediately re-inject after 20 minutes, I get the green chromatogram. It quickly goes to completion. My miscleavages are further cleaved, and so on. There is one interesting detail for those of you who are LC and MS specialists. The red chromatogram has the 3' end is a cyclic phosphate rather than phosphate. This is because the cyclic phosphate is semi-product and is further cleaved. Because those peaks, look at the 10 and 11 between green and red chromatogram, they are shifted. Because they have a cyclic phosphate instead of phosphate, they are also shifted in chromatogram. I thought that this is interesting and rather unpleasant. I don't want to deal with that. So that's maybe one of the complications. The other complication, look at the 50 mer peptide or RNA map. It has quite a lot of peaks, and I cannot stop the digestion. I cannot control it. There is no good inhibitor for RNase D1. So I say at this point that I am ready to abandon the idea of miscleavages because I cannot control the digestion, and it quickly goes to completion. There is yet another way how to do it, and this work was inspired by the paper from Genentech 2023. And they have proposed the method that you can take mRNA and you can insert complementary, let's say, DNA, and it will create duplex. The duplex portion is not a substrate for digestion. So if you strategically choose the sequence of your DNA to block especially the places where the Gs are accumulated, where there's a lot of Gs, and that portion would generate a lot of clips that are short and non-informative, you could block that portion from the digestion. So in this case, I show you 80 mer, the same 80 mer, the results you have seen already a few slides back. And I have 2 pieces of DNA targeting certain regions. And the original data that you have already seen are blue, light blue. If you are sitting in the back, you probably don't see it. And the red chromatogram is the one that the digestion was performed with those 2 blocking DNAs. There are few difficulties with this method. One difficulty is, well, you have a short duplexes. They are not necessarily stable even during your digestion. So I don't do 37 degrees C digestion. That would disrupt my duplexes. I do room temperature digestion. That's all fine. I also have the ionic strength of my digestion mixture high, so the duplexes are stable. The other difficulty for this method is that you are throwing in your mixture some additional oligonucleotides, your DNA blocking sequences, and they will obviously appear in your chromatogram. And it will look more complex. So what did I do? I chose my DNA to be labeled with C6 linker, and I hope that it will shift them to a much longer attention times. And it turns out that the C6 is not strong enough. I need to use some more hydrophobic tag to pull my DNA peaks, which is peak 15 and 14. Those are the 2 latest eluting peaks. I need to pull them further. But I can live with that, and I can adjust for that. But if you look at those 2 chromatograms, by blocking the sequence, this is the sequence at the bottom. There is a blue frame. That's the position where the hybridization happens. And I should be blocking the reaction, so my original 9B, 1B, 5, and 8 peaks should disappear. And they do. if you look at those two chromatograms. And I have 15 and 13. Those are the later eluting peaks. Those are my longer RNA sequences. So, good news, this method works. I produced my longer oligonucleotides that are now much more informative. I can do sequencing still. It's relatively easy. One little glitch in this chromatogram was that my 13 peak has also 13C analog. That's again the cyclic phosphate. So I have a signal, useful signal, that splits in now two signals. I think I can sequence both, and this is like a double confirmation. But if I leave this reaction to run another 20 minutes, my 13C peak disappears and converts into peak 13, the one that I want. So I claim that this method is actually quite useful. It has few wrinkles to iron out, but this could be very much used to do those peptide maps, maybe not only 100 mers, but if you are interested in your mRNA sequence, specific sequence, and you don't want to digest that one, and you can block that, and it will produce much longer oligonucleotide, and you can use it to perhaps investigating the single nucleotide polymorphisms or glitches in your mRNA synthesis, etc. So, I'm getting to the end of my talk. Ion pair reverse phase, I claim, despite that there are many other methods, it's the most efficient and most useful, especially because I also like having LC-MS capabilities. Separation selectivity depends partially on the sequence, but we understand how that works. And with these RNA-mRNA mapping or RNA mapping, I think that for these sgRNA, something like 100 or maybe 200 mer, this method of running RNA map using specific enzymes, it's actually quite promising. In my hands, it works rather well. And I also like this method of using blocking DNA to generate more longer sequences that I investigate rather than many of the very short ones, 2 mers, 3 mers, etc. Thank you for your attention, and I'm happy to answer your questions.
Great talk. Thank you for this. You mentioned Moderna paper from 2018, and I think they wrote their in-house script for data analysis for the mRNA mapping. Can you talk a little bit more about how you're doing the mRNA mapping? Because I think mass spec, every mass spec can generate the data, but I think the biggest bottleneck right now is how do we actually make sense of that data?
Yes. So first thing, you have a sequence, and you have to know the sequence up front. This is just a confirmatory sequencing. Second thing, what do you expect from mRNA mapping to give you? Is the goal to confirm your primary sequence? That's what we do with protein, so I assume you probably do. You may also look at some of the impurities and maybe glitches, sequence glitches, but that might be more advanced. So let's stick to the simple task. Everybody who does the mRNA mapping, they observe a lot of peaks. This is in part because we don't have many RNases that are highly specific. There are maybe 5, 6 people are coming with the new ones. Some of them have been presented as posters. I like that, RNase 4. They are specific enough. Some of them have many cleavage motifs, so no matter what you do, you still are generating something like 100 plus peaks, and many of them are short and non-informative and isobaric and redundant. And there is not much you can do with it except if you do painstakingly one RNase map and then use different enzyme and do second one and then combine the results, and you will get a higher sequence coverage. To do all of this, you better have a good informatics. So in Silico Digest, we'll give you a list of putative identifications. Then you have to have accurate mass. Then you have to have a software that will match the peaks. You can use the retention predictions like we did. That has actually some promise. And then you could also choose the mode of chromatography. So I like ion pair reverse phase because It has flexibility. I could use different ion pairing agents to either retain these short-mers if I want to, or perhaps resolve them based on the sequence. That I think would be useful. Hillick can do something similar. That's what Genentech like. They like Hillick method.
Thank you.
Go on the other side.
Yeah, great talk. Thanks much. And for that 100 more, actually we saw that from your presentation, and looks like it's hardly to have that peak resolution, right? In terms of a baseline. The curiosity about this, have you ever can get like essentially pure fraction of a full-length product, or the peak is just all overlapped? That means each fraction all contain the truncated one. What did you observe? Is there any possibility of isolation here? Thanks much.
So this is a question about purification, I understand. Once you have a resolution and you can resolve n-1, 2s, and 3s well enough, they will always contaminate your main product, and you will not remove them completely, but you reduce their content by 50%. If you don't have the resolution, which many of the methods for purification don't have the resolution, then you will co-purify them with your main product. There is no other thing that you can do. Unless you have a chromatographic resolution, you will not get pure product. There are things you can do. Ion exchange is amazingly efficient technique. Non-porous sorbents will do well. And then shallow gradients. And you could use, like Klaus mentioned, that they are using very slow flow rates. One of the reasons why peaks are getting wider is because we are way far away from optimal van Deemter conditions. If you do slow runs, the peaks are getting sharper and sharper and sharper. You can improve the resolution, but the expense is time. You will run it overnight easily. It will need hours and hours. Yeah, I can do it in lab scale purification. Let's say 50 millimeter ID column. That's a big column. I can do well. I cannot speak about big purification with 40 micron particles. That's beyond me.
Great, thank you. That was an excellent talk. I'm Jeremy from New England Biolabs. Thank you for mentioning RNase 4 as well. My question was really a curiosity regarding whether you tried MC1 or gusatavan or some of these other more generally specific nucleases, because trying to thread the needle there with T1 is always a challenge. So I just wondered if you had a comment on that. Yeah.
Absolutely. And one of my colleagues, who may not be in here, yes, we did try other RNases. We like them. We use them.
Hi. Very nice applications. I wonder if you have this blocking strategy for preventing the the RNase T1 to cleave. You showed us data of 2 non-neighboring blocking DNA blocks. Did you also try it with 2 really neighboring blocks? Is then the RNase T1 still able to cleave in between?
Excellent question. There are many information hidden in the data that I presented. One is that I actually use just an equimolar amount of the block. So if I guessed, and there were some small peaks that were actually generated from a full digest. Did I misjudge a concentration? And I had some unblocked RNA that was cleaved. So it would be safer to use an excess. That's one thing. Your question was, if the relatively short piece of blocking RNA, there is a close to the cleavage site, and there is just the blocking is not as efficient. The Genentech paper actually describes this very nicely. If the cleavage site is near the end, there is a good chance that the cleavage will happen at least in certain percentage. So you adjust your sequence accordingly. And I think that the reason why it cleaves is that we have a short piece of duplex, and this is dynamic. It opens, and close, and so there is a conversion between single-stranded form and duplex quite readily. So the cleavage can happen. So if you want to stop cleavage at that position, you better design an overhang of 2, 3, 4, if you can, nucleotides long of your DNA piece.
Thank you.
Hi, so my question is also about your block digestion method. So you mentioned you will use a very hydrophobic tag on the DNA to shift the DNA peaks. So my concern is, would that create some like steric hindrance problem to affect the hybridization between DNA and RNA?
I cannot really comment on that because I haven't tried yet.
I see.
I think it will be safe. I don't have to go crazy. I don't have to have a palmitoyl or anything. I just need a conveniently more hydrophobic linker that will shift my retention of DNA elsewhere. There could be some other ways how to remove my blocking DNA from the mixture, like biotin. Unfortunately, as I mentioned, the RNase T1 doesn't have any descent inhibitor. So if I remove the duplex, the reaction will restart and will go.
I see. Thank you so much. Excellent.